Okay, so I hope to make this short and sweet. You'll notice that the homework was over Chapter 9, not Chapter 9, Section 1 or 2 or any of that kind of stuff. The reason behind that is it's all pretty simple. I don't think there's really much that's new to you. So really you just have to know the vocabulary and how it works, what it actually means. So of course this whole chapter is about different transformations. Whether you're translating something, which is sliding it, reflecting a figure, which is flipping, or rotating it, which is just turning. Now, this next word, preimage, the preimage would be something like this. Okay, so here's our preimage. I haven't done anything to it, this is what I'm starting with. However, if I take this and I slide it over here, I have now done a translation which makes it our image. It's our ending result after doing a specific type of transformation. Now this will work with any of them. Line of reflection, well if I were to reflect this figure, a pre-image over a line, let's say it was here, it would be whatever line this was. In this case it's a vertical line, we could say it was the y-axis for instance. So moving on, if we go to actually using our line of reflection, we have a couple of options. We have the y-axis, which is what we have here, so this is our y-axis reflection. Okay, so when we're reflecting it over the y, we keep it the same distance away from the y and also the same distance away from the x. We're just going in the opposite direction. So what ends up happening is we take that point and now, as we slide it over, we're still keeping it up 4, but we're doing a positive 6 right there. So now our coordinates are positive 6, positive 4. So what happened? Well, when reflecting over the y-axis, and you'll want to write this down, keep y, change sign for x. Okay, so that's what you want to do. Anytime you're reflecting over y-axis, you keep y, change the sign for the x. So what do you think is going to happen when we do our x-axis reflection? I bet you can take a guess. So we will move this down, so we're keeping the same distance away. Now, the difference is that as we reflect it here, what do you think stays? The x. So it becomes negative 6, and now our negative 4. And actually, I think I moved it down a little too far. It goes up there. Yeah. Sorry. So, what ends up happening? Well, this time, keep x, change sign for y. Okay, so whichever line you're reflecting it over, that is the coordinate that you keep the sign. You don't change it for. Okay, so there's those two. Now, origin, which means this point here, if we're reflecting it over there. Well, what ends up happening is we're looking at how far away is this point from the origin, down and over, and repeat that. So, what we do is take that point, and we went down 4 and over 6, so we're going over 6 in the opposite direction, and down 4 again. So, we end up with a positive 6 and a negative 4. So both change sign. Okay, so that's when you're reflecting over the origin. All right, so there's that one. And now, which is over the line y equals x. Remember with this, our slope is 1. And our y-intercept is 0. So if you were to graph this, you go up 1 over 1, up 1 over 1, up 1 over 1, starting at the y-intercept, and then, of course, in the other direction. And there you go. Okay, what actually ends up happening with this one, I think it's a little bit hard to explain through a video, and hopefully when you come into class I can show you exactly how this works, but these will actually switch places. All right, so what we will do is instead of graphing negative 6, 4, it would become, dang it, come on, there we go. It would become positive 4 and then down 6. So it's there. So now what you will notice is that we weren't going how far away from the origin, is it? Okay, that's not quite what we're looking for. What we wanted to know is if we look at how this line or this point would have to go until it intersects with our line, we want to do that again in the opposite direction. All right, so what happens is we went down 4 and then down again another 6. So we went a total of 10 away. So if we're reflecting it, we want to go 10 away in this direction. So if you end up counting 10, you end up over here. There's your new point. Well, guess what? It completely inverted our coordinates. I hope that helps a little. If not, I can show you in class too. So again, this is same. I've already asked you to write this down, but if you didn't, do it. All right, now we have symmetry. For something to be symmetrical means it's a line of reflection. You can cut something in half. Okay, so for a shape, we could take this line here and slide it right there, right? And it cuts that shape in half. Each half is equal. Now if I take that out, so let's undo that, and then I move this one in. Well, that also cuts it in half, right? Or if I put this one in, this would also cut the shape in half. So we've got a lot of lines of symmetry, and what ends up happening is when you put all of the lines of symmetry in this figure, wait for it, we end up with a common intersection point. How about that? Isn't that crazy? So there we go. Check it out, man. So we have our point of symmetry right here in the center of the whole thing. And that's our point of symmetry, the common point of reflection. Now, not everything will have a point of symmetry. Okay, it depends on what exactly the shape is. Let's say if you have an isosceles triangle, for instance. Whoo, man, that's bright. If you have an isosceles triangle, this will not have a point of symmetry. Here's why. You can put in a line of symmetry. For this figure, we can take a line and put it right down the middle through that vertex angle, right there. Okay, it cuts it in half. It is equal on both sides. So when we have that, what you'll notice about this is that we can't add in another line anywhere else and make it still equal on both sides. If we tried to do it here, look at as I move this, we don't have any way to make this equal on both sides. And because of that, we have a line of symmetry, but not a point of symmetry. Okay, so we can reflect it just the one time, nothing else. Composition, so a transformation made of successive transformations. So a composition would be something like taking a shape, let's say I take a hexagon and I rotate it. All right, so I'm going to rotate it and then I'm going to slide it. So I have the rotation and the translation. Okay, so it's just successive. In the third section, we've got center of rotation. So that's a fixed point on which a figure rotates. All right, so the center, just what point is it actually rotating around? You have a couple of options. If you look at this figure, I can rotate this, and what you'll notice is that that center point of the pentagon is not changing. Okay, that's where it is rotating. So every point, every vertex is staying the same distance from this point. Where with this one, I changed it, and now you have this rotating around a specific vertex. So all of these vertices here are staying the same distance away from that fixed point. Angle of rotation, how far are you rotating it? So degrees. And then rotational symmetry. So if you have rotated it and the pre-image and image are indistinguishable, so they look exactly the same, you would have rotational symmetry. So let's say we took an equilateral triangle and then I rotated it a total of 60 degrees. Clearly that is not equilateral, but if I rotated it 60 degrees, it would still look the same. All right? So that would be our rotational symmetry. All right, now look, I promise it's the last one. I know, exciting, right? Tessellations. You all have seen tessellations before. They're up in my room. So it's just a pattern that covers a plane, no overlapping. So if we took, for example, I take this pentagon and I copy it. And I'm going to turn it a little like this so that the sides meet up. Okay, and then as I continue to do this, what will end up happening is they will eventually cover an entire plane without any overlapping. There. And we could keep going and eventually we would get this center part. Now, what happens with a pentagon is we can't use just a pentagon to fit an entire plane, because if you try to put this figure right here, you cannot fit a pentagon in here. So that's where these other names come in. One of them being a regular tessellation. Well, that would be if just one polygon that is regular. Remember, regular means all congruent. And it makes up the tessellation. You have uniform, the same arrangement of shapes and angles. So if it was triangle, square, all the way around. Or you have semi-regular. So that's a uniform tessellation by using two or more regular polygons. Okay? I know it seems like a lot. If you have questions, let me know. But for now, you are done with math. Well, for tonight anyway. All right, I'll see you soon.